All right, let's see how I can wake you up at that time of the day. So the most important word in this title is two words, actually. So because we are very much at the beginning, but still it's an attempt to get forward and consider a lot of collaborators of the work I'm going to present today and some related work. And actually quite a number of these people are in the audience, so you can talk with them yourself. So the question that I've been bordering with is, what are the fundamental phenomena that we need to care about in the social sciences? And that's maybe a subjective list that I'm going to present you, but I guess at least some of you would agree that among these points are points that have been identified by many other scholars as a very important issue. So homophily has been mentioned right in the last talk and also before. So the tendency to interact with similar people, but why is that happening? Social influence is a subject I will not talk about today, but cooperation in social dilemma situation will be addressed. Group identity will not be addressed, but social norms, social differentiation, and I will not talk about social structure, deviance and crime, social exchange and conflicts, but that's somehow on the agenda for future work. And let me explain you a little bit what is my approach towards trying to getting a better understanding of these kinds of phenomena. I'm trying to start off in a bottom-up way, trying to understand those phenomena as result of emergence and self-organization in social systems. That means as an outcome of individual interactions. And then the question is, what should be the assumptions we should make in such a model? And we should try to avoid putting into the model what we want to get out. So let's stay elementary. And some of the facts I think that most people would not question is that birth and death and reproduction are facts we can safely put into our models. Individuals need resources, there's competition, there's tool-making ability, perception, curiosity, emotions, memory, mobility, communication, learning, and teaching ability, the possibility of trading and exchange, and so on and so on. But if you would put all of these features into one single model, it would be possible in a simplified way somehow, and then we would come up basically with a computer game with a lot of parameters in it, and we would not be able to identify clearly anymore what are the cause and effect relationships. So what usually is the approach is we start simple, and then over time, and that could be decades actually, we get more and more sophisticated in our modeling approach. So we start off with looking at separate facts, as mentioned over here, and what are the implications of those. Then we look at binary interactions between those facts, and then we focus on a combination of three elements, and so on, in order to get a fundamental understanding. And here are some keywords that are highlighted. The ones that are shown in black are in one way or another inbuilt in the models that I'm going to talk about, but in a very simplified way. Still, it seems that we can understand certain phenomena based on these kinds of approaches. And let me start off with an example that actually brought me in contact with game theory. So when I did my diploma thesis, I was studying pedestrians, and it turns out that people are not just walking in a random way, but there is some order in the crowd, as you can see. So there's a segregation phenomenon. People walking into different directions are walking on different sides, actually. And this kind of behavior, in particular the segregation into lanes, of uniform walking direction can be understood with very simple models such as this one. We assume that there are repulsive interactions between individuals. Individuals enter at random locations and then they're walking forward, so there's a destination on the other side. We can see that through these interactions, a self-organization takes place and we find these lanes of uniform walking direction as a result of individual interactions. We don't have to assume over here that people would try to find optimal passes. We just assume very simple interactions. And in some sense also that reminds a little bit of Adam Smith's idea of an invisible hand, which basically states that markets self-organize. By the way, there are limits of this self-organization in the sense that not always self-organization would lead to a favorable result. We know crowd disasters are happening in pedestrian crowds sometimes, very sadly. And so self-organization can break down, or there could be other forms of self-organization that we would not like to see, as also we've seen there were problems with financial markets recently. So self-organization is not a guarantee of favorable outcome. Anyway, what I noticed furthermore was that there was a preference for one side that pedestrians had. For example, in continental Europe, most people tend to have a preference for the right-hand side, and in fact it turns out that this helps pedestrians to get around each other. So in many cases we have these situations where we face another pedestrian and then we can go either right or left. So we have two behavioral options as shown over here. We have two pedestrians, so in some sense it's a two-player game, and if both of them go right, then they manage to pass each other, and so there is a positive payoff, and if one of them goes right and the other one goes left, then they're standing in front of each other again. They have not succeeded, so there's no payoff, and they have to try again. And similar for the left-hand side, so we have this payoff matrix over here. It's well known to you, of course. It's a coordination game, and it's possible to come up with replicator equations which basically describe how the relative proportion of these two behaviors changes over time, assuming that the change would be proportional to the difference between the expected payoff of a strategy and the average expected payoff, and on the other hand proportional also to the number of people who could actually change the behavior. Now, plugging in this particular payoff matrix, we get the expected payoff shown over here and the average expected payoff shown over here. And then eventually we can find this replicator equation for the coordination game, which of course is well known to you. But let me nevertheless shortly summarize what it says. So there are three stationary solutions that are found by putting the time derivative to 0. One of them is 50% of people go to the right and 50% of people go to the left. And another solution is 100% of people going to the right, and the third stationary solution is 100% of people going to the left. Now, the next step in the analysis usually is a stability analysis, so you would determine the eigenvalues, and it turns out that, interestingly enough, this 50-50 solution, which seems to be a natural starting condition for the game, is not stable. That means a small variation in the fraction of people favoring one behavior over the other would eventually lead into one of those two stable solutions with the majority of people doing the same thing. So basically that establishes the formation of a behavioral convention, and that is something that I already formulated also with mathematical formulas in my diploma thesis. And of course, it's still relevant. Now the question is, what happens if we have other payoff matrices which are quantifying the success of interactions of people? And let me say at this instance that I personally believe that evolutionary game theory is a very powerful and flexible approach which has the chance to describe social interactions. So for me, it's in some sense the equivalent to elementary particle physics, which is an interaction theory for physical particles, but not claim that evolution game theory is as advanced in terms of the mathematical formalism, but I think we can get there actually. So I think this approach is quite promising. We'll show you a number of examples to motivate that further. And the probably most mentioned 2x2 game is the prisoner's dilemma, and we've heard about it many times also during this conference already. So that has a particular payoff structure which makes it a social dilemma. And in particular, in that situation, people have two options again, either to cooperate or not to cooperate. We say to defect. And the payoffs are chosen in a way that it's kind of tempting to defect and risky to cooperate, with the result that people are expected to end up defecting. In particular, if we plug in this payoff matrix into the replicator equation I have shown you before, so we would end up with what we call a tragedy of the commons, actually. And let me add that the prisoner's dilemma could be understood as a special case of public goods games with two players. Public goods game is also a social dilemma situation. We'll talk a lot about both of those two particular instances of social dilemma situations. So the question is, why is social cooperation so important and so interesting? Well, everything from public services and infrastructures over protecting our environment up to social benefit systems and language and culture require cooperative contributions. And as I said before, social cooperation is expected to break down if selfish rewriting generates better payoffs, so there is a temptation actually to defect. And the generation of public goods, in particular of society in many aspects, as I indicated before, requires to overcome this tragedy of the commons. It means the tendency of defection. And the question is, how can we do that? What mechanisms would do the trick? And many people have been working on this, a lot of bright and interesting contributions. Cooperation is one of the 25 most important scientific problems, according, I think, to science, and I think this is actually true. If social cooperation would not happen, then societies, I claim, would not exist, and we would have a war of everybody against everybody else. This is not something that I invented. You know the saying, homo hominis lupus, which is actually exactly the same thing in Latin. So the challenge is to understand how to overcome the tragedy of the commons. Taxes and the state enforcing cooperation are one solution, we know that. Taxes actually change the payoff matrix and the structure of the game, and then it would not necessarily be a social dilemma anymore, but that's simple. So the question is, are there better tricks, actually, or other tricks to reach cooperation even when the public goods game or the prisoner's dilemma are present? So before I want to go into the modeling, I want to list a few stylized facts that we observe in societies and that we want to reproduce by our models. I always tell my students that they should not just come up with a model, but first of all say what do they want to understand, what are the questions. And so we want to understand why individuals tend to agglomerate. We want to understand why individuals tend to segregate, and why the level of cooperation in experimental prisoner's dilemma and public goods situations is higher than expected. According to what I said before. I mean, it's usually, at least in the beginning, we don't see a tragedy of the commons, and then over time, well, it depends on the rules. The other thing that we know is individuals' behaviors are partially determined by the social environment. And social environments persist much longer than an individual contributes to it. So a company exists for a long time. By that time, many people have changed their jobs and so on. And social systems adapt continuously. Now, the model that we came up with is combining two different mechanisms. One is imitation of the best performing neighbors. And you can see over here 3 different colors. Red is representing defectors, and blue is representing cooperators, and in between there is white, empty space. And that will be needed actually for the modeling of success-driven migration, and we'll go into this later on. So let's have a look at the situation where we start off with 50% cooperators, and people are imitating the best performing neighbor. Now what you can see is, actually as expected, defection is spreading, but as we have assumed, deterministic imitation will over here. The situation freezes after a short time, and that's it. We'll talk about the impact of noise imitation later on. So, imitation doesn't do the trick of spreading cooperation and increasing the level of cooperation. Let's have a look at success-driven migration. So in that case, if it doesn't come with imitation, then of course everybody sticks to the behavior, but people could change their location. And we stay with 50% cooperators. Let's see what happens as a result of the success-driven migration. So how does it happen actually? People would look within a certain radius around their current position. What would be maybe a better location if they moved over there? So they do something like virtual interactions, and if they would earn a higher payoff, then they would move to the best location within this radius. And so what you can see as a result of that, there is actually an agglomeration process. So cooperators tend to stay close to each other, and close to these cooperative clusters, there are the defectors. So we have something like agglomeration here, and also segregation. It's not very pronounced, but let me state that both of these mechanisms are not capable of increasing the level of cooperation. So in some sense, both of them fail. So we would not expect that combining those would do anything interesting. Why should mobility actually have a positive effect on cooperation? But in fact, if we combine the two mechanisms, it turns out very surprisingly that now the level of cooperation is increasing enormously. So we have large cooperative clusters over here. This model society keeps changing. There's still some defectors, again, at the boundaries of the clusters. And so this is something quite interesting, and we need to understand that better. But obviously, cooperators are doing well in the cooperative environment, and this cooperative environment seems also to stabilize cooperative behavior. So it's a little bit like what I described to you before, that there's this social milieu effect, that the environment is influencing people's behaviors, but at the same time, the social environment is made up of the people's behaviors. So this is something we find in this oversimplified model, but still, I think it's interesting. But let's go a little bit more into detail. So why is this happening? Why is the combination of these two mechanisms so successful in promoting cooperation? Well, let's have another look at success-driven migration in separation. So no imitation here. But we look at the influence of different kinds of payoff matrices, and what you can see is that even though in all these simulations we start off with homogeneous distribution of behaviors in space, over time there is a pattern formation. There are different patterns depending on the payoff matrices. You can see in this case there is segregation, very similar to the lane formation I've shown you before. Also, there could be repulsive agglomeration, so not all the space is used, but again, the two different behaviors would end up in different places. It could be maybe called ghetto formation. And over here is a case of attractive agglomeration, where the two behaviors end up in the same locations, actually. But not all the space is being used. So it's a clustering phenomenon. And we have done that also for the parameter combinations that are relevant for the prisoner's dilemma. So all what is below this diagonal line is the prisoner's dilemma. So R, P, T, S are the usual abbreviations for the payoffs in the prisoner's dilemma. So T is temptation, P is punishment, R is reward, and S is sucker's payoff. And above this diagonal line, we have the snowdrift game. What you can see over here, red are the parameter combinations where we stay with a uniform distribution over time. So it's a very small parameter area, actually, where we don't have pattern formation. In all the other parameter areas, actually, pattern formation occurs, which means agglomeration and segregation. And one can do that even with many, many more strategies, as is shown over here, for two simulations, which I won't explain in more detail, but you can see, I think there were 10 different strategies over here. I can see a clear tendency of same colors to end up next to each other. So we have actually this birds of a feather flock together phenomenon, which is called homophily. So success-driven migration is promoting such a birds of a feather flock together phenomenon. And I think imitation is doing that also to a certain extent, but somehow success-driven migration is promoting that very much. And of course, there are some analogies to Schelling's model. You have certainly thought about that. But we haven't put that model in. It's basically coming out from the success-driven migration, which is using the same payoff matrix that specifies the interaction outcome between individuals. Now, the question is, how robust is this finding? And so people have been asking, what happens if a defector manages to intrude a cooperative cluster? Would it be possible to erode cooperation from within? And so we introduced mutations. We are starting off here with a city where everybody cooperates in the beginning, and then forget about success-driven migration for a moment and just look at imitation of the best neighbors and at these mutations that would flip the behaviors of individuals with a certain probability. And what you can see under these conditions is that even though everybody starts off cooperative, we end up with a higher and higher level of defection. It means again, we have this strategy of the commons that we started off with. So actually, it's very bad news, but also that's something that we expected, that noise would actually be harmful for cooperative clusters. We have also been looking at other kinds of noise, in particular long-range relocation. So sometimes people are moving from Germany to US and vice versa, or Japan, or whatsoever. We can see again, if we combine imitation of the best neighbors with this long-range random relocations, and we end up with a tragedy of the commons. That means noise is really very harmful in the imitation-only scenario. So the question is, what happens if we combine imitation of the best performing neighbors with success-driven migration? That's a scenario that I'm showing you over here, and to make it a bit more interesting, we're starting off with defection only. And when I asked my PhD student whether he'd ever done such a simulation, he said, well, we don't even need to try that because nothing will happen. And then after a few weeks, I asked again, have you done it in the meantime? He said, no, and then I've been sitting next to him and waiting what would happen. And in fact, he was right for 5 minutes. And so we start off with defection only. You can see through these long-range relocations, the cluster dissolves, but most people defect. But then after a very large number of iterations, we find by coincidence this formation of a supercritical cooperative cluster. So it needs to be large enough. For that, we need to be wait long enough. And however, if that happens, then you can see cooperation is spreading quickly in the system. And that was really exciting, and we coined it the outbreak of cooperation, because really for a very long time the level of cooperation stays ridiculously low. Just a few mutations that make it different from zero, but it's enough to make this coincidence of cooperation in a small neighborhood happen after some time, and once that happens, a very quick spreading of cooperation takes place. And it doesn't require a particular initial condition or some luck, it happens always. So we have done it many times. You can see over here the standard deviation. So it ends up with cooperation. So that is really fantastic. The question is, does it happen only in the computer? So is it a theoretically nice finding, but practically irrelevant? And so we were comparing this with experiments, and here is an experiment which does not directly relate actually to the prisoner's dilemma, but again it's a two players interaction. We called it the route choice game, where people go from an origin town A to a destination town B every day, and there are two alternative roads, a freeway and a small road. And everybody would like to use the freeway, but then this gets congested somehow, and it's better if cars are distributing of these two alternative roads. However, the system optimum is kind of reached only by a sacrifice of those people who are using this small road over here. So why should they be willing actually to use the small road? And so the question is, what's happening in this experiment? We've done it for a different number of players, in particular also for a two-player version. Here, this graph shows you where the route choice game is located as compared to the prisoner's dilemma, the chicken game, battle of the sexes, and so on and so on. The situation is like this. So in principle, from the system's point of view, it's good if we have one player using the freeway and the other player using the small road. But the player on the small road, of course, gets a much smaller payoff, so he gets upset. He also wants to use the freeway, and if the other person is not willing to switch to the small road, then basically both individuals end up on the freeway, and it's very bad for both players. Now here are some experimental results. So we have run that really for a large number of iterations. That is very important, as you can see, because people have a tendency to use the freeway, which is the decision to, but on the other hand, sometimes they're trying the other alternative. And then sooner or later it happens that, again by coincidence, they are taking turns. That means one of them was on the freeway, the other one on the small road, and then in the next iteration they happen to do it the other way around. So that means the one who was on the freeway before is switching to the small road, and vice versa. And that turns out to be very favorable because it establishes a system optimum, and also it's user optimal. So somehow people learn, hey, this is a good solution actually for us. It's performing much better than if we end up using the freeway. And so there is an outbreak of turn taking in this case, again after a very long time. Let me go into another model before I show you another experiment. So one criticism we've heard about this migration model was that the way we implemented the success-driven migration. Because we basically tested an environment where people would move, assuming virtual interaction. So we assumed basically people could assess how nice the environment would be if they moved there. Of course, the environment could change over time quite quickly, but still, somehow people could guess what would be a good environment and what would be a bad environment. So, Ernst Fehr, for example, asked, isn't that the green beard effect? And I said, I don't think this is the issue over here. But then we came up with another model together with Carlos Roca, who is sitting here in the audience. And that model does not assume that people could actually detect what strategy other people are playing or find out about their payoff. So we have been very strict over here, assuming that individuals would just have a memory of their previous experiences. And actually a quite bad memory, so they're forgetting over time, and basically they remember the highest payoff and the lowest payoff, but as you can see over here, also, if that's a long time ago, they wouldn't remember it so much. And then they have a certain expectation, which is between the minimum and the maximum payoff. We call that expectation parameter the greediness of the individual. So if you expect to get 60% of the maximum remembered payoff, then you're 60% greedy in some sense. And then somehow this defines the satisfaction level, so the expectation regarding the payoff. If the payoff that the individual receives in the next time step is above this expectation level and people are happy, if it's below, then people are dissatisfied, and then the more dissatisfied they are, the more likely they are to change either their location or their strategy. So in some sense, it's a generalized win-stay-lose shift rule, one could say. It's also related to the concept of satisficing. So individuals are not trying to find the optimal behavior, just have certain expectations regarding how much payoff they would like to get. And if they're happy, then they do the same thing. And if they're unhappy, they're trying to find a better place in the world or find a better behavior to get a better payoff, which makes, I think, a lot of sense. And then based on this, we again find actually that there is agglomeration of cooperators, and that this agglomeration comes also with an increased level of cooperation. So again, we have a co-evolution over here between spatial organization and behavior. That's something which is related to the correlated dynamics that previous speakers have been referring to, so correlations are really the essence over here. And now the question is, how does that actually depend on the parameters that we're choosing? So we were particularly interested in the effect of greediness. And we said, okay, let's start with a very low level of greediness and see what happens. And it turns out it's not good for this model society, so level of aggregation and cooperation is low. In particular, the cooperation is a very low level because people don't have any expectation. They're just happy with what they have. So why should they make an effort? Now, if they're getting more greedy, then they can only be happy by really reaching something. And reaching something here happens by cooperation in this public goods game. So cooperation pays off somehow. That allows individuals to get a better payoff. And so that is actually stimulating cooperation, as you can see. So some greediness is good. For society, it causes agglomeration and cooperation, a combination of which we call social cohesion. And so given that situation, one could think, okay, if increasing the greediness is increasing the level of cooperation, then why shouldn't people get more greedy? Because it turned out to be good in the past, right? So it would be logical that people would get more and more greedy. So we go up this line over here, and that is the greediness. And you can see for a long time, cooperation, agglomeration are fine, but then there is a certain level, something like a tipping point, where suddenly people are hard to satisfy. Because it's very difficult to find conditions under which people could reach their expectations. So they're on the move all the time, social agglomeration falls apart, and also social cooperation cannot happen anymore. So we find something like a breakdown of cohesion over here, and it reminds a little bit of the rise and fall of society stories that we can find in some history books, when we can read that some high cultures have suddenly disappeared, surprisingly, and there's still a controversial discussion about the mechanism leading to that. I'm not claiming that would be the ultimate explanation, but at least it's a stimulating finding, also in the context of the financial market instability. Now, we have done an experiment based on this model very recently, together again with Carlos Roca, Charles Efferson, and Sonja Vogt. And we've compared a situation with migration in a spatial grid with a situation without migration, which is our control experiment. And at least now voluntary migration. And you can see that for the control treatment, we find the expected result. People start off with a certain level of cooperation, but soon get frustrated and end up with a very low level of cooperation. So we find the tragedy of the commons that I've been starting off with. However, migration can keep a high level of cooperation alive in the system. So really, that is quite interesting. And you can see in this evaluation over here that there's quite some difference in the average payoff in between the two scenarios, with migration and without migration. And actually, mobility is key to success. So I think that is important to consider when you're trying to understand cooperation. In fact, the relevance of mobility is increasingly recognized, I would say. So you've heard Ernst Fair referring to this paper yesterday. And also here's another paper by Richardson and Boyd, which highlight migration. So somehow there is an increasing recognition that mobility can be quite helpful for the evolution of cooperation. But also costly punishment. Costly punishment is something that many people have investigated, and so let's have a look at the situation where we have a bigger parameter space, so not only the possibility to cooperate and to defect, but cooperators could also punish defectors, and we call those moralists. And we are also considering defectors who are punishing defectors and call them immoralists because they're behaving in a hypocritical way. Now, as indicated, punishment is costly. So the big question is, why would people punish at all? Why wouldn't we find a second-order free rider dilemma? First-order free rider dilemma refers, of course, to people not paying a contribution to the public good, and that's why they're free riding. Second-order free rider dilemma refers not contributing to the sanctioning of non-cooperative behavior. Yes, in fact, it would be much cheaper if other people would do the punishment for you, because punishment is stressful, it may require a lawyer, can be costly, and so on. So certainly, it's usually not for free. So one of the big questions over here is, why don't we have a second-order free rider dilemma? And let's start off with the discussion of the well-mixed situation, where we have these four strategies. could be in a grid, but then if people are interacting with the grid, they would interact either with everybody in the grid, I mean, the neighborhood would be very large, or people would be interacting with randomly chosen neighbors from all over the grid. That would both be implementations of a well-mixed situation. And it turns out that in that situation, again, a tragedy of the commons is the result. And actually, it's even more tragic than that, because the mechanism is as follows. Somehow, there's a competition between cooperators and moralists. Moralists have to bear extra costs for the punishment, and so they have a lower payoff, which means that neighbors would not imitate them. They would rather imitate cooperators, so cooperators would be spreading, and moralists would eventually disappear. But once cooperators are losing their friends, the moralists, because they're not doing anything harmful to them, actually. They're also cooperative. But once the moralists are gone, actually, there's nobody anymore who would punish the defectors. So then we end up with the normal prisoner's dilemma, where, of course, defectors are spreading because they don't have to bear the contribution to the public good. So once the cooperators have crowded out the moralists, they're burying their own grave in some sense. So this is really tragic. But now look what happens if we have neighborhood interactions within a limited neighborhood. And we're starting off over here with all the four different strategies, 25% each, randomly distributed all over the place. And what you can see is that in the first stage, actually, defection is spreading. So there's a majority of red-colored individuals, so non-cooperative behavior really is spreading over here. But you see another thing, that again we have a segregation phenomenon over here. And that turns out to be crucial, because as a result of that segregation, now cooperators and moralists don't have to compete directly. They're segregated, okay? Now they're actually both competing with the defectors. Here is a good example, okay? So blue and red are struggling with each other, and red and green are struggling with each other. And we know that the cooperators don't have a chance against the defectors. But moralists can punish defectors, and so what happens is that defectors spread as compared to the cooperators, but the moralists are spreading as compared to the defectors. And so, while in the beginning we have a majority of defectors, and in the second stage we have a majority of cooperators, in the end we have a situation where moralists prevail. So that means we have just the opposite outcome. Rather than defection by everybody, we have a lot of cooperativeness in the system, and people are also punishing non-cooperative behavior. And here is a simulation that shows you that dynamics. This is quite unexpected, but in a very simple way, it explains why we don't have a second-order free-rider dilemma. So you can see that spatial interactions, again, are key for the understanding. And so in the social sciences, we should spend much more attention on spatial interaction of all kinds. There are also many other interesting phenomena in the same model, such as an unholy symbiosis of moralists and immoralists in certain parameter areas, namely over here. So here is so-called phase diagrams that show you what would be the possible outcomes as a function of parameters of the model, such as punishment, fine, and cost, and also the synergy factor that goes into the public goods game. So in particular, you can see that you have to have a large enough fine in order to promote the spreading of moralists. And on the other hand, if you spend a higher cost on punishment than that, you won't reach a difference. So it's very important to identify the right threshold. And also there are other interesting effects, such as actually a few defectors are promoting the spreading of moralists as compared to cooperators. Now we've also heard questions about antisocial punishment as compared to pro-social punishment. We have been looking here at another experiment where people could migrate according to the success-driven rule that I've indicated before. And over here, people don't either cooperate or defect, but they have a certain probability of cooperating or defecting. So that probability can be a continuous variable that is changing over time. So what you can see as an outcome of this dynamics as a function of certain parameters is that if you don't have this punishment option, and basically defection prevails, but with punishment option there is quite a significant parameter range where suddenly cooperation can spread, and actually the spreading of the cooperation is correlated with the punishment of defectors, which is suddenly occurring even if we start with 0 punishment of defectors. And then, on the other hand, there's another area in the parameter space where we have actually antisocial punishment. That means punishment of cooperators. So both of it can be actually understood. And in fact, depending on the parameter combination, we can find the emergence of pro-social punishment, starting from 0 punishment in the beginning, or the emergence actually of antisocial punishment. So that is really interesting. So in a society where there is no punishment and no cooperation in the beginning, through the co-evolution of cooperation and punishment, somehow punishment and cooperation will suddenly spread. Now, social norms is another interesting subject actually to talk about. And many people have discussed social norms in the context of cooperation games. I would actually contradict to this to a certain extent. I think these are two different problems, and social norms is a separate subject to talk about, and of equal importance actually to understand social behavior. I'm a little bit under pressure of time, so I'll speed up a little bit. What we have done over here is that we have assumed two populations with incompatible preferences. So population 1 prefers to behavior 1, and population 2 prefers to show behavior 2. It's rewarding to show the preferred behavior, but also to show the same behavior as an interaction partner that is randomly chosen with a certain neighborhood. That is the assumption of this simulation over here. It turns out to be of a stack-hunt kind of interaction. I'll come back to this later on. And now we can find that there are kind of 3 possible outcomes. One outcome is that everyone tends to show the own preferred behavior, kind of a laissez-faire society. But that could also be a situation where population 1 sets the norm. That means one population 2, namely, would adapt the behavior to the preferences of population 1. And there's, of course, also the other situation where population 1 adapts to population 2. And what we also find is that not only the outcome depends on the relative size of the populations and on the reward structure, but also on the initial conditions. So the outcome is history dependent, as we know that actually from social norms. That is very interesting as well. And then finally, if we are assuming local interactions, and we only within a small radius, then we actually find the emergence of local cultures. So blue and red are actually the preferred behaviors, but you can see that we are ending up with areas which are red and yellow, so one population has adjusted locally to the other population. And also we have areas where we have blue and green, where the other population has adjusted. And actually that's the situation that we find in the world, that we have local cultures, local norms, and so that comes out quite naturally over here. Now the most interesting case, however, is when we have a situation where actually behaviors would coexist, but where people at the same time apply something like an adaptive group pressure. So assume that people are shy to put pressure on others if there is not a majority for that behavior. Then they would just tolerate what other people are doing. But assume that there is a large majority in the neighborhood of a certain behavior, people would start putting pressure on people not behaving according to the majority behavior. This is what we mean with adaptive group pressure. And what happens then in a scenario where actually both preferred behaviors could coexist, we find that after some time, again by coincidence, we find local majorities. And that local majority will build up a local group pressure. And eventually, that causes a breakout of a social norm under conditions where we would not expect it to happen through those feedback effects. Again, that would not happen without noise in the system, but we know that actually social systems are quite noisy. Now, as I indicated, the game we're talking about here in the context of understanding the emergence of one of several possible norms in a situation where one norm is not preset. This is the multi-population stack hunt game over here. But one could look also, of course, at multi-population prisoners dilemma games, snowdrift games, harmony games, and so on and so on. And you can see there's a large variety of different outcomes that we can find. And I'm skipping over a few transparencies over here, but in particular, there are a number of social and biological mechanisms that are transforming a prisoner's dilemma in a way that promotes cooperation in a normal prisoner's dilemma's game. The question is, do all those mechanisms also promote the formation of social norms? And that would be important in order to see, is the emergence of cooperation the same thing as emergence of social norms? It turns out no, not all mechanisms would promote the emergence of social norms. Some of them would, actually. So starting off with a prisoner's dilemma, a transformative effect by direct reciprocity, that means repeated interactions, by indirect reciprocity, reputation effects, and punishment actually does promote the formation of social norms. But also it can happen through other mechanisms, such as kin selection. The prisoner's dilemma would be transformed into this area of the harmony game, or we would end up through certain kinds of network interaction in the snowdrift game. And then let's have a look at what happens in these kind of different situations. So here, for the prisoner's dilemma, we find, of course, the breakdown of cooperation. For the second game, we find the formation of shared behaviors, that means social norms. But it could also have the formation of subcultures, where each population basically does what it prefers. And just remember, that was actually expected for genetic inheritance. And in fact, cultural and ethnical correlations are quite obvious in our world. And then finally, there are situations where conflicts would result in actually even revolutions, where we can have sudden transitions by very small parameter changes in the payoff structure, sudden transitions from a situation where one population would do what the other population prefers to a situation where that population would do what it likes. So that is the typical revolutionary situation that we're facing, for example, at the moment in Northern Africa. Now, I could end up actually with some real-life examples also from traffic theory. So it turns out that trying to optimize traffic control locally at each intersection actually establishes something like a social dilemma situation, and such a control would not work well. It means it does not establish a system optimal situation because there's not enough coordination between neighboring traffic lights. And in order to overcome this dilemma, you need to have better rules that actually take into account what is happening in the neighborhood. You can see over here that we found actually rules that allow to synchronize traffic and reach a very well coordinated situation, again by self-organization. And in some sense, that's a very nice practical application of game theory, which actually benefits everyone. I mean, people who use public transport, people who use their cars, pedestrians and cyclists, and also it benefits environment. So let me finish with this. Thank you for your attention. I'm happy to hear your questions.
Two-dimensional model is simple in comparison to real life. And we know from physics that the results may be different if it's not two-dimensional. And real network is without dimensional limitation. Do you try to do something to check all this simulation in more than two-dimensional model?
Absolutely, that's a good point. And in context with our publications, we have actually checked quite a number of different scenarios, and also, in particular, we have replaced spatial 2D interactions by network interactions, and the findings that we've made stay basically the same. So what I have been reporting about today is not sensitive to the many variations that we've been looking at.
Let me ask a question from an empirical perspective. I mean, you have covered a lot of ground, starting with stylized facts, and then you presented a number of models that reproduce these stylized facts. But one will argue these stylized facts are known. And what one would like to see now are new predictions from these models, testable predictions.
Right, okay. Let me answer as follows. First of all, I would love to see a book that actually is summarizing all the major stylized facts of the social sciences. That would be extremely helpful, because that would be a very good orientation for everybody who's building models, and kind of the ultimate challenge to reproduce as many of these stylized facts as possible. So at least I was trying not to pick just one or two stylized facts that happen to fit the model, but to first identify a long list actually of different findings that that are out there, and then try to reproduce them all at the same time. But I agree, the ultimate challenge is actually to formulate predictions and to test it in the laboratory or in real life. And actually, for that, the phase diagrams that I've presented today, I mean, this is a phase diagram, for example, or also this is our 4 phase diagrams. They somehow say what kind of system outcome is expected if we increase this parameter or that parameter or so. Of course, I would not expect that the model is predictive in the sense that this line is exactly here, because real life is messy. But if we would make experiments, I would expect at least that the empirical phase diagram bears some similarity with this, and lines may be shifted or so. But overall, if the empirical phase diagram that hopefully one day we'll be able to identify through a large number of experiments, I would hope that that would look similar, and that would really be a breakthrough, I think. We have been successful doing that actually for traffic flows, where there's a number of different kinds of congestion. Stop-and-go waves, homogeneous congested traffic, and a number of other kinds of congested traffic. And we came up with a theory that was predicting what were the flow conditions under which we would find this kind of traffic congestion or that kind, and so on and so on. And then years later, we got hands-on data sets, actually, of real freeways. It took another few years, actually, to evaluate the data, but they were fitting quite well to the theory. So I hope we can do the same kind of exercise for these kinds of models over time. Not necessarily all in my lab, but I'll be happy to collaborate with others or advise any experiments done in that direction.